Welcome back to Tech 293, How to Break Stuff. Today is Tuesday, January 19th, and today I'm going to make two different videos. The first video is going to be the first session where we start talking about materials science. Remember last week I mentioned that the first couple of weeks of this class are devoted to materials science, which is kind of an atomic or molecular look at the way materials are put together, and that informs the way that they're going to behave at the large or macro scale, which is what we're interested in the majority of the course after the first couple of weeks. So what we're going to do is start today by looking at the atomic and molecular bonding that happens in materials. And next time we're going to look at lattice structures. And then the time after that, we are going to look at specific classifications of materials and how the properties of those materials is impacted by the bonding inside those materials. So first things first, today we are going to start by talking about different types of bonding inside the materials. Some of this I know you've seen before in high school, chemistry classes, things like that, but some of that I think will be new as well. In the second video today, we are going to actually do lab 1. So I'm going to go down to the lab, the plastics lab, Turner 122, and I'm going to bring my camera and video setup with me, and we'll actually go through lab 1, and I will call out all the data, and you will write down all the data, and you can use that data to write your lab report for lab 1. So just kind of like we were lab partners, and I was doing the measuring and calling out the data, and you're recording all of the data. So think of it kind of like that. All right, so with that, let's go ahead and get started. All right, so this is the material science portion of the class, and we're going to talk about different kinds of materials. I'll mention them today, but we'll save most of that discussion of the different types of classifications of materials for another day. I'll just mention them today. Today, the emphasis is really on the types of bonding. And I know that you have seen some of this before, but we're going to review it and probably go into a little bit more detail than you have seen in previous, maybe chemistry classes in high school. And the reason this is important is because it's important to know how materials are put together, because that affects what's going to happen when we break them, or how they break, or how they fail, and how we can load them. And so it's important that we understand how these materials are put together, and what types of bonds they have, and what they look like on a molecular level, because it has a significant impact on their macro behavior. So that's why we're interested in the types of bonds and how they are structured, because it impacts the mechanical properties. So we're going to talk about some of that today as well, and we'll continue talking about those mechanical properties in future days. Also, toward the end of this video, we'll talk about the phases of matter, because actually the type of bonds and the type of molecules that the material is made of has a pretty significant impact on whether a material is a solid, liquid, or gas at, say, room temperature or at any given temperature. All right, so I'm going to mention these different groups or classifications of materials, and we'll talk more about this in a subsequent video. But the different materials that we're going to talk about are metals and ceramics and polymers and wood and composites. Now, really, the last two are they're almost kind of like miscellaneous categories, because really wood is actually a natural polymer. We'll talk more about what a polymer is in a little while in subsequent classes. But a wood is actually just a type of polymer that is from nature, and a composite is just kind of a mishmash of lots of different stuff. It's two or more different types of materials that are usually intentionally combined together to get the best properties possible. And here's a further categorization that I'm not going to spend much time on right now, but suffice it to say that we can break down each of those 5 categories into subcategories and Throughout this class, we will talk more about most of these. We'll talk about different kinds of metals and different kinds of polymers. I know you talked about that in TEC 285 also, if you have taken that. So you discussed the plastics more in TEC 285, but yeah, we will talk a little bit about it in this class as well. And we'll talk about the others as well. We'll talk a little bit more. You know, probably we don't talk a whole lot in this class about ceramics and composites, but a little bit. We'll talk a little bit more. And we'll do some testing on a plastic composite material in lab 4. And then wood, we're going to do testing on wood. Mainly, wood's important because it's so common in the building and engineering industry, mainly because it's plentiful and it's cheap, frankly. All right, so that's all I need to say about that classification of materials for now. We'll come back to that in a later class session, just 1 or 2 days from now. All right, so this should look familiar. This is a periodic table, and we can generally divide the periodic table into sections. The materials on the left 2/3 that are kind of in the yellowish goldish color, we call those metals. And the materials that are in the upper right corner in light blue here, we call those non-metals. And then there's another word, actually a couple of words, that describe these in between that are kind of in tan, I don't know, the salmon color right here. This graph calls them metalloids, but there's another common word that is commonly used in the computers industry. If we were in person, I'd have you guess it, but often these kind of salmon colored materials are often called semiconductors because they have some properties of metals and some properties of non-metals. So they're kind of in between, and those in between characteristics are kind of exploited by the semiconductor industry to make all kinds of modern electronic devices, especially silicon and germanium. These are the two most commonly used in electronic devices. So the reason I bring this up is because where an element is located on the periodic table determines the structure of how the atom is put together. Specifically, it determines the valence electrons. And you've probably heard that term before. Valence electrons are the outermost electrons. Does it have one electron that's in the outermost shell going around all by itself, or does it have two? That would be the case over here. Group 1A, these are your alkali metals. You may have heard that before. Group 2A, that's this column right here. These are the alkaline earth metals. These have 2 electrons in their outermost shell. And then you've got these all the way over here, and these over in the far side. These are sometimes called your halogens or your noble gases, and these have full valence electrons. They have 8 electrons in their outermost shell. So these are happy or content, or better to say stable. These are stable. But everything else would really prefer to have a full outer valence electron shell. They'd be more stable, or we can say that they'd be happier. All right, so the way that materials bond together is determined mainly by its valence electrons. So we're going to talk about each of these types of bonds in more detail, but I can tell you right now that if you have a metal element and a non-metal element, if they bond together, that's going to be an ionic bond. If you have 2 non-metals that are bonding together, two non-metals, if they bond together, that's going to be a covalent bond. And if you have 2 metals, 2 or more, if you have metals that bond together, that's going to be what's called a metallic bond. And you might not have heard of metallic bonds before, but it is a type of bond that is distinct and unique from ionic and covalent bonds. And we're going to talk more about that in a little bit, just a little bit, because that gives metals some of their important characteristics. All right, so what we're going to talk about in today's video is 4 types of bonds. And I just mentioned 3. Those 3 that I just mentioned, ionic, covalent, and metallic bonds, are all atom-to-atom or atomic level bonding. But there's another type of bond that's also really important that determines the properties of materials, and that is molecule to molecule. Quick refresher, atoms are smaller than molecules. Molecules are made of atoms bonded together. So as those atoms bond together, they form a molecule. Molecules can be as small as 2 atoms bonded together, like H2, hydrogen, or carbon monoxide, CO. Lots of examples. NaCl, that's another example of a molecule. They could be as small as 2 atoms bonded together, or they could be thousands of atoms bonded together. All it means is a bunch of or collection of atoms bonded together. That's what a molecule is. And then once you have a molecule, then materials like a block of wood has, I don't even want to venture a guess, but we're talking millions to billions to trillions. I don't even want to guess how many zeros we're talking, but lots and lots and lots and lots of molecules that are together. And the way that those molecules are held together determines the mechanical properties of the materials. So this is why we care. This is why it's relevant to this class. All right, so atomic bonding, the quick refresher, the modern view of the atom, at least the view that is not, yeah, I have to be kind of careful here because the most modern view of the atom is really given by quantum mechanics, but that's not actually that helpful to visualize. So the view of the atom that is most helpful to visualize is called the Bohr, B-O-H-R, named after a person in the early 1900s. The Bohr model of the atom, which is what most people, you're probably thinking of. It's a nucleus that consists of 1 or more protons and some number of neutrons. Not all atoms have neutrons, but some neutrons with the protons in the nucleus, and then the electrons spinning around the outside, kind of orbiting around the outside. So that's a pretty helpful model to visualize, and it's accurate enough for our purposes. And the goal, if you can say that, I don't know. I think it's kind of funny to say that because atoms don't have ambition. Like they don't have free will. Like they're not like saying, I need to steal another electron. Like they're not plotting to steal electrons. So it's probably more accurate to say that they are most stable when they have a full or complete valence outer electron shell. So think about that. If it makes you happy to think about atoms seeking happiness by having a full valence electron shell, hey, that's great. If that works for you, that works for me. So the atoms bond to each other, atom-to-atom level bonding, by either ionic bonds, and we'll talk in more detail about each one of these, but generally an ionic bond means that one atom is stealing an electron from another atom, or covalent bonds wherein atoms are happily sharing the electron or electrons. And then the other one that you may not be as familiar with is metallic bonds, where the whole collection, you have millions or more of metals nuclei, and they're all sharing, they're pooling this huge pool of electrons. So it's like this giant pool of electrons, and the electrons are free to move around within the metal, which is, I'll say this later, but that's why metals are so good at conducting electricity, because the electrons in the metal are really free to move around. All right, so it is unique and distinct from ionic or covalent bonds. All right, so first, ionic bonds. This is where you have one atom that has one or only maybe a couple of electrons in its outer valence electron shell. And frankly, it would be more stable if it just gave those away. And you have another atom over here that is just missing one or a couple of electrons from its valence electron shell and would be more stable or happier if it could just get a couple of more electrons. And the more an atom wants to steal electrons, there's a word for that, it's called electronegativity. So if an atom is highly electronegative, that means it really is trying to pull away electrons from other atoms. A good example is fluorine. Fluorine is highly electronegative. It really wants one more electron to fill up its valence electron shell. All right, so it does, chlorine's another good example. Chlorine is also highly electronegative. And probably your prototypical example of an ionic bond is table salt, sodium chloride, where sodium has one valence electron, chlorine has 7, so it really wants one more, and sodium wants to give one up. And so sodium is pretty happy to just give one of its electrons to chlorine, and now we have NaCl, sodium chloride, otherwise known as table salt, plain old table salt. All right. There's a name for the atom that gave up an electron, and there's a name for the atom that took an electron, because the thing is that now they're no longer neutral. Now we've got a positive ion and we've got a negative ion that are bonded together because of their positive and negative charges, and they attract. All right, so the words we use for that are anion and cation. And here's the way, I'm going to give you a way to remember these. All right, this is the way that I learned a long time ago, and it has stuck with me. So I'm gonna share this. When you think of when you're trying to remember this, what I want you to think of is a dead cat. All right, you can't forget that. You can't. I mean, you try as you will. You can't forget a dead cat. I'm telling you to think of a dead cat, and the reason why I'm telling you to think of that is think about a dead cat pictured in the cartoons, like some cartoon character cat, and it got hit by an anvil or something like that. An anvil fell on its head. How do they depict a dead cat in the cartoons? Well, usually they do something with its eyes. And how do they show a dead cat's eyes in the cartoons to tell you it's dead? Well, usually the eyes of the dead cat are shown as either X's or pluses, right? That's the way I remember seeing cartoons anyway. So this is helpful because you can associate through what I've just told you, and I don't think you'll forget this if you think about this at least for 2 seconds. I don't think you'll forget this. A dead cat has eyes that are shaped like pluses. And in ionic bonds, the ions that are positively charged are called cations. So that just leaves the other ones. You just have to remember what the other one is. The other one is an anion, so you'll have to remember that's the opposite, and that's the negatively charged ion. All right, so remember these two things. Remember what an anion is and what a cation is. An ionic bond is fairly strong. It's not as strong as some of the other bonds that we'll talk about, covalent bonds, but it's relatively strong. And there's lots of different combinations in terms of elements. Any element that would like to give up one or more of its valence electrons. So any element in those first 2 columns of the table would be happy to give up some electrons, and any elements in the last couple of columns, except the very last, the couple of the last columns, except the very last column in the periodic table, would be happy to take one or more electrons to fill up their valence electron shell. So there's lots and lots of different combinations of ionic bonds. So before in the picture on the slide before, I just showed an anion and a cation, and once we have a negative, a cation and an anion, we have a positive charge and a negative charge, and so they are bonded together. But in reality, this doesn't happen usually between just two ions. Usually you have a whole bunch of them. You have a whole bunch of material. And so these tend to form 3D structures that are called lattice structures. And lattice structures are actually really common to lots and lots of different materials. In fact, next class is all about lattice structures. That's the second day of talking about materials science. So next time, we're going to talk a whole lot more about lattice structures because they're that important. All right, but this is just an overview, an intro today, and I'm going to tell you that lots and lots of ionic bonded structures tend to form lattice structures. And lattice structures are these repeated organized patterns that are connected, in this case by ionic bonds, in 3 dimensions. So these are solid structures that are repeated, anion, cation, anion, cation, anion, cation, in all 3 dimensions. All right, so think about these 3-dimensional structures. All right, so because these bonds are fairly strong, the materials themselves tend to be fairly strong. However, they don't tend to be very ductile. In other words, you can't really stretch them very much, because if you try to stretch them or if you try to hit them, they tend to just snap or just break, or we call cleave. Cleave, just split down the middle. And there's a very good reason for that, because if you think about what's going to happen if you hit it or you try to deform it in some way, what's going to happen is you're going to have anions next to anions in the structure and cations next to cations in the structure, and like charges repel. And so here's an example here. If you had a atomic level hammer, which obviously you don't, but this is a good example of what's going to happen. So if you hit this structure, then it's going to cause relative movement between the different layers in this structure. And so if you hit it, then you're going to end up with something that looks like this, right? Because you've now moved some layer of the material against other layers of the material. And now you have this cation next to this cation and this anion next to this anion, and they repel. And so instead of just smoothly deforming like polymers will, instead of that, this is just going to crack and cleave or split. All those words mean kind of the same thing. So it's just going to split because they're not very ductile. So ionic bonded materials usually form lattice structures, and those structures tend to be strong, and they tend to be rigid, and they tend to be hard, but they are not very ductile. And if something is not ductile, we say that it is brittle. All right, I've said probably all of this. So ionic bonding materials, they usually form lattice structures, that is repeated, ordered, 3-dimensional structures, and they tend to be very strong. Here's an example. This is what table salt looks like, and this is what it looks like in 3 dimensions. If you zoom in on it on an atomic level, this is what you'd see. And there are different types of lattice structures. Here's a quick, I'll throw down this term, and then we'll talk more about it in the next session. This is called a face-centered cubic lattice structure. And there are a bunch of different kinds of lattice structures, and we'll talk more about those in the next class. So I want you to know these general properties of ionic bonded solids, all right? And we're going to give similar descriptions for covalent bonded materials and metallic bonded materials. Fortunately, there will be some similarities, so you won't have to memorize all of them. There'll be some similarities here, so it'll actually be easier to memorize the differences between them. All right, so because ionic bonded materials tend to have fairly strong bonds between them, that makes them pretty hard because the atoms in that lattice structure can't slide in that structure very easily, like we just showed with that microscopic hammer, right? They tend to be good insulators for both electricity and thermal. They don't conduct electricity and they don't conduct heat very well for the same reason, and that is that the electrons are pretty tightly bound to their atoms, and they can't move around. The atoms can't move around easily. The electrons can't move around freely. Also, the atoms can't move around freely either. Just lost my internet connection. Not sure what that was about, but now I'm back. So we were talking about ionic bonded solids, and we left off by talking about how they are transparent because the electrons are not moving around. And if you don't have a whole lot of electrons moving around, they don't scatter the light as much. So they tend to be transparent materials. They also tend to be rigid and brittle, like we just talked about a couple of slides back. And they also tend to have a pretty high melting temperature because they are held together with pretty strong bonds. And so to break those bonds and melt it, you have to apply quite a bit of heat to break those bonds and get it to turn into a liquid. All right, next we're going to talk about covalent bonds. And if ionic bonds are all about one atom stealing an electron from another atom, then covalent bonds are all about sharing. So covalent bonds are when the atoms play nicely together and they each would really like a full valence electron shell, and if they shared them, then they could each have a full valence electron shell, so that's what they do. Good example of these are H2, or that's hydrogen, N2 for nitrogen, F2 for fluorine. Lots of these have covalent bonds. Also hydrocarbons, all of your methane, butane, octane, pentane, all of those are all covalent bonds. Lots and lots of examples of covalent bonds. Sharing electrons between atoms. All right, you can have, like I just gave some examples, the atoms that are sharing could be the same atoms, or they could be different atoms, like carbon dioxide, where you've got one carbon and two oxygens, and they're bonded together by sharing electrons between them. Diamonds, another example. Polymers generally are held together. Individual molecules within the polymers are held together by covalent bonds, and many, many, many others. Covalent bonds tend to be very strong. They tend to be stronger than ionic bonds, and whereas ionic bonded solids tend to almost always form lattice structures, covalent bonded solids, sometimes they do and sometimes they don't. We cannot generally say that covalent bonded solids form lattice structures. Some of them do and some of them don't. There isn't an easy pattern to remember. If they do form lattice structures, like some do, then they tend to have pretty much the same mechanical properties as the ionic bonded lattice structures do. All right, so the material properties I'm going to get to in a slide or two, they're going to look very, very similar to the ionic bonded materials, because if the covalently bonded materials form lattice structures, then we can say pretty much the exact same things about them that we said about the ionic bonded materials. If the covalent bonded materials don't form lattice structures, then it just varies by material, and we can't make a whole lot of generalizations about the materials, other than to say that covalent bonds tend to be stronger, at least individually, than ionic bonds in general. Carbon does some really cool things, so I put a slide in here to talk about carbon. So Maybe you know some of these. If I asked you what are some materials that are made primarily out of carbon, you could probably come up with some of them. Some of them are here on the slide, but there are actually a couple of others. There's two others at least. So one of them is diamond, and diamond forms a covalent bonded lattice structure. So this is the unit cell for diamond over here. You can see it's pretty complex. And these are covalent bonds in between these carbons. And it does form a sort of lattice structure with this as the unit cell. So it's complex. And it's very, very strong. And it is, you probably know, it is the hardest material in nature. So that's kind of a real extreme. Another material that carbon tends to form if it's not subjected to as much heat and pressure over time, carbon also forms the basis of coal. And there's different types of coal. There's lignite, and there's anthracite, and there's a couple other types of coals. Coal is also carbon, but it does not have a lattice structure. And coal, I don't know if you ever held it in your hands. I actually have, I'm not going to get it out, but I went to, this is quite an aside, but I went to a coal mine once, just on a tour, and I went down in the mine, and it was very interesting. And anyway, I don't really want to get it out because it's messy. It would get all over my hands and all over my computer. But I've got a few rocks, chunks of coal directly from the mine. They let us grab a bunch of chunks, basically whatever we could carry out. You know, coal's not expensive, so they let us take whatever chunks of coal we wanted to carry out. But anyway, coal does not have a lattice structure, therefore you can break it apart pretty easily. It's not very strong. Another form of carbon is graphite, what you might be writing with. I really prefer mechanical pencils nowadays. Mostly have mechanical pencils, but that doesn't make for a very good demonstration. So the writing part of these pencils is made from graphite. And graphite is pretty cool because graphite is made from two-dimensional sheets stacked on top of each other. And those two-dimensional sheets, those flat sheets, are called graphene. And you may have heard of that before. It's been in the news in the past couple of years. Graphene has some really cool properties. Graphene is an individual sheet like this. This is a layer of graphene. This is a layer of graphene. So is this. All stacked together, we call it graphite. But those graphene sheets are pretty interesting. That's what actually makes graphite easy to write with, is because as you're writing, the individual layers of graphene are shearing off and staying on your paper. And that's what makes graphite easy to use to write with, because these layers can easily shear off of the graphite and stay on the paper, and you can read what you wrote then. But in the past few years, people are experimenting with individual layers of graphene, and a lot of them have experimented with rolling these up into a tube, which is usually called a carbon nanotube. You may have heard of that before. And carbon nanotubes made out of graphene have some pretty wild properties. They are actually stronger than steel, like on a per volume basis. They're stronger than steel. They have better conductivity than copper, and they're harder than diamond, again, for their size and volume. It's pretty amazing what you can do with these carbon nanotubes. Anyway, so what I'm trying to get at here is you can have the same material, carbon, and you can combine it in different structures in different ways, and you can get very, very different types of materials, all based on the bonding. So this is why we're talking about this right now. It's why we're talking about bonding between atoms and eventually between molecules. We'll get to that. All right, I want you to realize that you can have materials that have both ionic bonds and covalent bonds together in the same material. Here's an example of that. This is real common in lots of different natural materials. It's called calcium carbonate. And you can think of this as basically being like the chalky substance. It's mainly what chalk is made out of. You can write on it. It leaves the residue on the chalkboard. It's also, if you ever, cut like a marble or limestone or something, if you cut rock, you kind of get that same chalky substance. And it's the same thing. It's calcium carbonate. So the point I want to make is just that lots of materials have both ionic and covalent bonds in them. And they'll also have intermolecular bonds as well. So you can combine all these different bonds in different ways. Here are some examples. This on the right is a hydrocarbon. That means it just has hydrogen and carbon in it. And if we count the carbons, 1, 2, 3, 4, 5, 6, 7, 8. This is a hydrocarbon with 8 carbons. And there's a common name for this that I'm sure you've heard before. This is octane. So this is the most common constituent of gasoline. And gasoline is actually a mixture of lots of different hydrocarbons. But the most common one in gasoline has 8 carbons. But in your gasoline, you're going to have hydrocarbons of lots of different lengths. 6, 7, 8, 9, 10, 11, 12 carbons, lots of different chain lengths. On the left, you probably recognize this. This is DNA. And within DNA, the individual chains, so these are really, really long, these chains that go around like this in a helix, these are held together with covalent bonds. And then this chain is held together to this chain with intermolecular bonds, which we'll talk about in a little bit. All right, so this, I already mentioned this, but covalent bonded materials, if they form a lattice structure, then we can say pretty much the same things about them that we said about ionic bonded lattice structures. So this is actually the exact same, almost the exact same slide as we had a few slides ago. So if the covalent bonded materials form lattice structures, then they are hard, and they are good electrical insulators and thermal insulators for the same reason. They're also transparent, they're rigid and brittle, and they have a high melting point for all the exact same reasons that we talked about earlier. So I won't belabor the point, but it's the same reasons as we talked about before with ionic bonded lattice structures. If the covalent bonds don't form lattice structures, like the hydrocarbons or the DNA or thousands and thousands of other examples, then we can't really make any generalizations other than to say that the individual bonds are pretty strong. Now we get to metallic bonds that are important to all metals, all different kinds of metals. And what's interesting about metals is that they are very good at sharing their electrons. So it's just this sea of electrons, or this pool of electrons. And I didn't make those terms up. The sea of electrons, that's generally how metals are described. So all of the metal nuclei in the material, they're all kind of sharing the electrons. And the valence electrons are free to just kind of float around in the material, and they're just being shared by all of the metal nuclei in the material. And so that's what makes metals really good conductors of electricity and of thermal energy, heat, because those electrons are free to move about and transfer between one part of the material and other parts of the material. So the way we think about this, I often think about this like stacks of cannonballs. And this we'll talk more about that next time when we talk about lattice structures. But when you think about these lattice structures, and metals do form lattice structures, think about those lattice structures as like stacked layer upon layer of cannonballs or something like that. Any type of stacked spherical object will work. And yeah, so oftentimes when I think about lattice structures, I think about something like this. It's not a ball pit, so it's not the best example because this is not quite as ordered. And also the balls themselves can move around very easily, which is not true in a lattice structure. The individual atoms in the lattice structure can't move around very easily within the lattice structure like these balls can in a ball pit. And also these tend to not be as regular, periodic, organized, structured as lattice structures are. But it works, you know, as you're thinking about these like stacked cannonballs, it kind of works to think about a ball pit. All right, so lattice structures, we're going to talk a lot more about those in the second session as we talk about material science. That'll be in our next class. So ionic and covalent and metallic structures, they can all form lattice structures, but they don't always form lattice structures. Ionic bonded materials almost always do. Certain kinds of covalent bonded materials do, and metals almost always do. But they tend to be a little bit more ductile. Metals tend to be a little bit more ductile. And the reason is because of the metallic bonding. And the metallic bonding, the way it works is that the nuclei of the metals are bonded to the sea of electrons, but the nuclei of the metals are not bonded to other nuclei of the metals. And that's different than ionic and covalent lattice structures. Because remember in those ionic, I've showed you the picture of the ionic bonded lattice structure with the ions, the positive and the negative. Metals aren't like that. The metals, when metals bond, there isn't an anion and a cation in a metallic bonded solid. All of the metal nuclei are just bonded to the sea of electrons. They're not bonded to the other nuclei. So that is why metallic bonded materials tend to be more ductile. It's not as, they don't move around as easily as, you know, say a ball in a ball pit, but they do tend to be more ductile because the nuclei are not bonded to each other. So they can stretch more easily. Here's some more. This is a picture of a lattice structure, and these are the electrons that are just kind of in this sea of electrons, and they're free to move and kind of just float around. So metallic bonds are a little different than ionic and covalent bonds because of that sea of electrons. And the whole material is held together due to the attraction between the metal nuclei and the sea of electrons. So that's what's actually bonding together. And I just said this, the metal nuclei or the metal ions are not bound to the other metal nuclei or metal ions. And so they can slide past each other more easily into form, which is what makes metals relatively ductile compared to other types of crystalline lattice structures. Crystalline is another word that just means an ordered periodic structure, a solid structure. So these are a little bit different. So the metal properties, metal solids, tend to be only moderately hard because as you press into it, now you probably can't do it with your fingernail, but if you have a sharp object and you poke into it, they're only moderately hard compared to ionic and covalently bonded lattice structures because the atoms are free to slide past each other if you apply a big enough force. They're also very good electrical conductors and thermal conductors because those electrons are free to move around and transfer their energy. They tend to be opaque because the electrons tend to interfere with the photons of light and they scatter the photons of light. And they tend to be relatively ductile, like I just said, because layers of the structure can slide past one another if you apply sufficient force. And this is all relative, but only a moderate melting temperature, because those individual bonds between nuclei are not particularly strong. So a review, I would be asking you this if we were in a class together. So review, make sure that you know the 3 types of atomic bonding, and you can tell me some of the properties. You should be able to tell me which types form lattice structures, which types tend to be more ductile, and which types tend to be most brittle. So the 3 types that we'll answer this briefly. The types of bonding that we've talked about so far, we've talked about ionic and covalent and metallic. Which types form lattice structures? Well, they all can. Most ionic bonded structures, most ionic bonded solids form lattice structures. Some covalent bonded solids do, some don't. So it's hard to make generalizations about covalent bonded solids. And metals almost always do form lattice structures. Which tend to be most ductile? That's the metallic bonded materials, because the nuclei aren't bonded directly to each other, only to the sea of electrons. Which tend to be most brittle? That's the ionic and the covalent. Both of them tend to be quite brittle. Like I showed earlier with that hammer. What happens as you try to get them to slide past each other, you end up with ions that repel each other. All right, so the next thing is intermolecular bonds. You know what, this is a good time to take a quick stretch. All right, there's only a little bit more. There's just one last type of bond that we're going to talk about. And we're almost through talking about bonding. So we've talked about atomic level bonding, atom to atom, and now we're going to talk about molecule to molecule. So you might have a molecule over here made up of atoms that are bonded together through ionic or covalent. Mostly we're talking about molecules that are made of ionic or covalent bonds. And same thing over here. We might have the same or a different molecule over here, and there is an attraction through different mechanisms between those molecules. And that attraction is what lets it form solid materials. Otherwise, if there was no bond between them, then you just have a bunch of molecules that are just kind of scattered everywhere. It wouldn't take the form of a solid substance. There are a few different kinds of, come on, not going. There we go. Okay, all right. There are a few different kinds of intermolecular bonds, and we're going to make some generalizations and talk about 2 of them in particular, all right? So intermolecular bonds are also known as what are called van der Waals forces. Van der Waals forces are forces between molecules, all right? And oftentimes these are created when you have these molecules that are not perfectly sharing the charges between them, right? So we talked about covalent bonds, and we talked about how atoms share the electrons between them. Well, in actuality, oftentimes they're sharing, here's a good analogy. Oftentimes the way atoms share electrons is kind of like the way my kids share toys, which is to say, not very evenly. Sometimes it's more even than others. So the general type of van der Waals forces, or intermolecular bonds, might be kind of like the way my 5-year-old plays with my 7-year-old. All right, so usually they do a pretty good job of playing together and sharing things, but it's not a perfectly even distribution. All right, so if my 7-year-old, she's a girl and she's crazy. If my 7-year-old daughter is playing with my 5-year-old son and she really wants a toy, she's going to take it from him. So I wouldn't say that they share it perfectly evenly. So that's kind of like the way oftentimes covalently bonded materials work. All right, so in this molecule right here, just this molecule right here, This is octane again. So we've got carbon, that's this gray atom, this gray atom, this gray atom, this gray atom. There's 8 of them. And the hydrogen, that's the white spheres here and here and here and here, and all these white spheres. Well, the carbon and the hydrogen are about equally electronegative. That means they each want the electron about as much. However, carbon is a little bit more electronegative than hydrogen is. So carbon wants it a little bit more, wants that electron a little bit more. So as a result, you've got places in this molecule that have a little bit more negative charge and other places that have a little bit more positive charge. All right, so since carbon wants the electrons a little bit more than the hydrogen does, out here on the edges of the hydrogen, say here and here and here, you end up having a slight positive charge. And in here, say right here and right here and right here, near the carbons, you end up having a slight negative charge because the electrons are more likely to be there because carbon wants it a little more than hydrogen does. All right, so you've got partial charges on this molecule. Similarly, you've got, this is not an identical molecule, but this is also a hydrocarbon. Same thing over here. You've got a slight positive charge here and here and here and here, and you've got slight negative charges here and here and here. So what happens is, if these two are next to each other, they're going to have a slight attraction to each other. That attraction is not nearly as strong as a covalent bond or an ionic bond or even a metallic bond, but it is an attraction nevertheless between these two. And so the positive charges, the slight positive charges on this molecule, here and here and here, are going to be attracted to the places like, say, here and here and here that are slightly negative in this molecule. So they'll just kind of fit, it's almost kind of like this. They just kind of fit kind of neatly together, kind of like that. And these are bonded together kind of like that. All right, so that's basically how these intermolecular forces usually work. It's in general. Van der Waals forces, intermolecular forces, for our purposes in this class, they mean kind of the same thing, and that's mainly how these things work, all right? Slight positive charges on one molecule are attracted to slight negative charges on another molecule, which has a relatively weak bond between these molecules, causes a relatively weak bond between these molecules. Okay, yeah, I think I said everything on this slide. All right, so it's a lot easier to see in the three-dimensional drawing that I just showed, but you can kind of see it in the two-dimensional. So this is still a hydrocarbon, so these are carbons in the middle, these are hydrogens on the outside, and you've got slight positive charges here and on every hydrogen, and slight negative charges in the middle here. And so these slight positive charges are attracted to the slight negative charges. It's harder to see in 2 dimensions. I think it's a lot easier to see in 3 dimensions. I just backed up a slide. So you can kind of see how this molecule could almost kind of fit into this molecule. It's harder to see in 2 dimensions because molecules are not 2-dimensional. Definitely not 2-dimensional. All right, but another thing I want to say is that we'll talk more about phase of material in just a couple of slides, but the longer the materials, the longer the molecules, the more opportunity you have for those intermolecular forces. And as you have stronger and stronger intermolecular forces between these molecules, then it takes more and more and more thermal energy to melt them. So they tend to be solids at higher and higher temperatures the longer and longer the molecules are. All right, and I'll give you some examples in just a second. But here's a molecule. Is this octane again? 1, 2, 3, 4, 5, 6, 7. Yeah, this is octane again. So octane is a liquid. You know that because at the gas station you pump it into your gas tank. But this one down here, this is, I don't even know what the word would be for this. This is a whole bunch more carbons. I don't know if this one has 12 or 16 or whatever carbons, but this would be more like a sticky solid, maybe more like an asphalt or something like that at room temperature. So this has more, it's almost more like a zipper, you know, and there's more bonding places between the molecules, and so this tends to be a solid at higher temperatures because it takes more thermal energy to break those bonds. All right, here's an example proving what I just said. Here are some different hydrocarbons. These are all hydrocarbons, meaning they only have hydrogen in the middle, carbon in the middle, and hydrogen surrounding them around the outside. So your smallest hydrocarbon is methane, otherwise known as natural gas, and it has a melting temperature. I mean, you never see natural gas as a solid. I never have. You'd have to get it really, really, really cold to get methane, natural gas, to be a solid. You got to get it really, really, really cold. But what I want to point out here in this table, as you get more and more carbons, the molecules get longer and longer and longer, and thus you get stronger and stronger intermolecular bonds because they all add up. You know, you have individually they're very weak, but as the molecules get longer and longer, you have more attraction between these molecules through intermolecular or van der Waals forces. And so as the chains get longer and longer through these hydrocarbons, then the melting temperature gets higher and higher, and so would the boiling temperature, to the point where if you get a really, really, really long, you know, tens of thousands of carbons, then it doesn't really even melt. It just softens, and that sometimes that blows people's mind. They're like, how can a material not melt? And a good other example is like wood. Does wood melt? No, you can't get a wood to melt. We'll talk about why some polymers, remember wood is a natural polymer. We'll talk about why some polymers melt and some don't in a later class. But yeah, it's true. It's true. Some things will melt, some things won't melt. And in general, the longer the chain, the less likely it is, and the higher the temperature you would need to cause it to soften or melt. Okay, that's enough for now. Okay, there's one more type of, a special type of intermolecular forces that we need to talk about, and that's called hydrogen bonding. And hydrogen bonding, it's nothing different than what we just talked about. It's just a much stronger version of intermolecular forces or van der Waals forces. All right, so what happens is if you have bonds between certain molecules or certain atoms in the molecule, certain atoms are very highly electronegative. And those three that we generally consider to be extremely highly electronegative are nitrogen, oxygen, and fluorine. NOF, just remember NOF. That'll help you remember which three are highly electronegative that cause hydrogen bonding. So generally, if you have a molecule that has one of these three elements in it, nitrogen, oxygen, or fluorine, these are very highly electronegative, and they pull a lot of the share of the electrons over to it. So a good example is H2O. If you have water, the oxygen wants those electrons a lot more than the hydrogen does. So you have a relatively strong partial positive charge next to the hydrogens, and you have a relatively strong partial negative charge on this side where the oxygen is. And so in water, it's called a polar molecule. So in say a bunch of these molecules together, like in a cup of water, they tend to line up. So you've got this kind of repeated structure where the the water molecules tend to line up where this oxygen has a partial negative charge, and so it's attracted to the partial positive charges from the hydrogens in this molecule right here. So the negative side of this molecule is attracted to the positive side of this molecule, and the positive side of this molecule is attracted to the negative side of the next molecule, and so on and so forth. So even though it's a liquid, you can stir it, you can swish it up, and they will move around because it's a liquid. There is an inclination for these molecules to line up and for the negative charges to be attracted to the positive charges of adjacent molecules. All right. So the analogy here, this is like not just my 5-year-old and 7-year-old sharing a toy. This is like my 5-year-old and 12-year-old sharing a toy. And if the 12-year-old wants the toy, the 12-year-old is just going to take it and doesn't really care what the 5-year-old thinks or wants. So oxygen is like the 12-year-old, and hydrogen is like the 5-year-old. And the oxygen, or if it was a nitrogen or a fluorine, it would do the same thing. It just takes the electron and doesn't share it very evenly. That's a decent analogy, I think. All right, other than that, it's pretty much the same thing. It's these partial charges on the molecules, and they're bonded to each other through these weak intermolecular forces. And what this does, this actually has a pretty significant impact on the mechanical properties, like the boiling temperature and the melting temperature. In fact, it's kind of crazy. This is responsible for making water a liquid at room temperature. If there was no such thing as hydrogen bonding, then water would be a gas at room temperature. And life, as we know it, either wouldn't exist or it would be very, very, very different from what we know it. Because, our bodies rely on water being a liquid. If water was a gas at room temperature, then our bodies as we know them, could not exist. All right, so last thing here, we're going to talk a little bit about a couple of factors that influence the phases of matter. We were just starting to get into that with intermolecular forces. So we know that elements combine together into molecules, and molecules combine together to make a material, and that material is either going to be a solid or a liquid or a gas. For now, ignore plasma. Plasma is the 4th phase, but it's kind of irrelevant for our purposes. So the phase of a material, obviously it's impacted by things like temperature. It's also impacted by pressure. You know this because if you go to Denver, Colorado, things boil and freeze at a slightly different temperature, which is why on the back of a box of brownie mix, you will see high elevation instructions because things boil and freeze at different temperatures. So it's impacted by temperature and pressure, but also things about the molecular structure of the material impacts whether it's going to be a solid or liquid or a gas. And I've mentioned that already a little bit. So 2 things that I want you to know about the molecule itself that impacts whether it's going to be a solid or a liquid or a gas. Number 1 is, independently of anything else, the size of a molecule impacts its phase. So all else being equal, if you have longer molecules, then they tend to have higher melting and boiling temperatures because they have stronger intermolecular bonds between the molecules, which means that to break those bonds and to cause it to melt or to cause it to turn into a gas, you need to break those bonds through adding thermal energy. So it takes more energy to break those bonds, the stronger they are, and the longer the molecule, the stronger those intermolecular forces. All right. So examples of those are the hydrocarbons. I already showed that table a few slides back. These are all hydrocarbons: methane, Methane is the simplest one, it's CH4, and then butane has 4 carbons, octane has 8, and wax has hundreds to thousands of carbons. And as you go from these, you go from something that you have to get really, really, really cold just to turn it into a liquid, much less a solid, to wax, which is a solid at room temperature, and you have to get it pretty hot just to melt it into a liquid. All right, and then independently of everything else, the strength of those intermolecular attractions has an impact on the phase. For example, if you have intermolecular bonds that are relatively weak, let's say, well, let's just leave it at that. If you have intermolecular bonds that are relatively weak, then that substance is going to boil at a lower temperature than if you have a substance that has very strong intermolecular forces like water. Water is a small molecule, but it has very strong intermolecular bonding between them. All right, so the smaller the molecule tends to depress the boiling and melting temperatures, but the strength of the intermolecular bonds tends to elevate the temperature at which it melts and boils. All right. Oh, here's a good example. All right, hydrogen sulfide and H2O look very similar, but one has oxygen. That's one of the atoms that really is very electronegative. So these molecules have much stronger intermolecular bonds. In fact, they have hydrogen bonds, which again are a type of intermolecular bonds. And so H2O has a much higher melting and boiling temperature than hydrogen sulfide does. All right, that's going to wrap things up for the first session on materials science about types of bonding inside materials. In the next session on Thursday, we're going to talk more about lattice structures. And we're going to talk about how lattice structures form and how they are arranged physically inside the material and how that affects the mechanical properties of that material. So that's what we'll do on Thursday. But in the very next video for today's session, we're going to go down and do Lab 1. So I'll see you in the next video for Lab 1.